Okay, so this is another fun little example. What we have here, particles A and B, which each have equal mass, which are initially not sliding over their smooth guides. And the T-shaped member here is spinning with a rate of omega. And we're told that the mass of the guides and the pulleys are negligible, and that the influence of friction is likewise negligible. And basically what we want to find, given this scenario, is the angular speed of the arm as well as the speed of particle B at a later instant if the distance r increases. Okay, so to help us out with this, I'm going to draw a free body diagram for my system, keeping it as large as possible. And in this case, if I make the system inclusive of everything here, what you'll quickly realize, and maybe in this case I should say everything I'm going to make it inclusive of is the rope and the two blocks, that the only real force acting on this is some reaction force R here, as well as the weight of block A and the normal force that comes up from that, and also a normal force at block B and the weight of block B. Now at first glance a lot of these forces cause issues, but I want you to think about something here. As you've seen in a number of things in this chapter, we're trying to determine if we can use something like conservation of angular momentum. Generally speaking, if we look at forces that could cause moments, that can be an issue, but we'll note that many of the forces that appear in this diagram don't cause moments. Specifically, we know R points through point O, so we know it does not create a moment. This weight also points through point O, and so that doesn't create a moment. If we note that particle B is constrained to move along a vertical guide, it's relatively easy to determine that the normal force at B has to be 0. And likewise, if we note that A doesn't move in the vertical direction, then the weight and normal force here have to create equal and opposite moments. The net result here is that even though we have many forces acting on this system, the sum of moments about point O actually has to equal 0. With this in mind, I can say that the angular momentum about point O at state 1 has to equal the angular momentum about point O at state 2. Now, even though I'm going to use this and apply this to the angular momentum of the system, the thing I want you to keep in mind here is that B contributes no angular momentum. In other words, I only have a contribution from A. So in this regard, I can say H about O at state 1 is going to equal R1 cross MV1, and I can substitute this as being a distance if I call this the E sub R direction, and I'll call up, just to be consistent, the K. Then I'm going to have this is equal to R1, so it's going to be R1 in the E sub R, cross the mass times the velocity. Initially the particle's not moving with respect to the arm, but the arm is rotating, so this will give me R1 times omega in this case, the E sub theta. So if I work this out, E sub R cross E sub theta is K, so I'll have M times R1 squared times omega in the K. Now at the second state, we've moved out some further distance, and so this is going to give me now R2 in the E sub R cross M times now R2 dot in the E sub R plus R2, let me not squeeze it in here on you, but R2 times omega 2 in the E sub theta. The R dot term comes in now, of course, because A could be moving radially outward. The key thing to note is that even though that dot term there, it's going to quickly go away because E sub R cross E sub R is 0, and so what I'll be left with here is M times R2 squared times omega 2 in the K. If I go ahead and equate both expressions here for angular momentum, I'll have that M times R1 squared times omega in the K is equal to M times R2 squared times omega 2 in the K. I can use this and cancel out the common mass, the common K vector, and what I'll get here is a result that the angular speed post the motion is going to be equal to R1 divided by R2 quantity squared times omega. Now that I have that in hand, I want to determine the speed of particle B. Note that it didn't come up in these computations, so I have to determine another way to find that. And the way I'm going to determine is using the work energy expression. Note that we have a change in position here and we want to have a speed, so this is a very logical thing to move forward with. So if we want to compute, first of all, the initial kinetic energy, we'll note that the only motion initially is the spinning of block A, and so we're going to have 1/2 times the mass of block A times its initial speed squared, and keep in mind its initial speed is R1 times omega, and we'll square that. The potential energy for the system, I'm going to go ahead and determine based on two separate datums, so I'll define a datum for each block. I'll put ahead up here VGA is equal to 0, and down here I'll put VGB is equal to 0. Using this 2-datum setup, one datum for each beam, I can note that initially the potential energy for the system is given to be 0. The non-conservative work done moving between states 1 and 2 is going to be 0, because if I look at these forces here, none of them actually create a force that produces work. Pardon me. T2, the kinetic energy of the system after the motion, is going to have to account for the total speed of block A, so I'm going to have 1/2 times m. Its total speed squared is going to be r2 dot squared plus r2 times omega 2 all squared. So we'll end up with something that looks like that. And then I'll need to account for the potential energy of block B, the kinetic energy of block B. So in this case I have 1/2 m. What is the kinetic energy of block B? Well, we can come back up to our diagram here and note something very important. Namely, we have a rope length constraint relating the speed of block A and the speed of block B. This rope length constraint is a little different than what we've seen before because the only component of speed that actually matters is the radial component. Namely, if we called this a distance SA and this a distance here SB, what I could say is that SA plus SB is equal to a constant, which tells me that VA plus VB is, I shouldn't use V, I should say SA dot plus SB dot is equal to 0. The key thing here is that this does not account for the rotation of block A, only the translation out. And so what this means is that R2 dot of block A has plus R2 dot of block B has to equal, in this case, 0. So if I'm going to square that term and account for the R2 dot of block B, what I'm going to have here is 1/2 m times another R2 dot quantity squared. In other words, the radial component of block A has to match the speed of block B as it moves up. The final thing I need is the potential energy. We'll note that the potential energy of block A does not change during the motion, simply block B, and the amount it changes by is given by mg times the amount that block goes up, which is R2 minus R1. I can take these 5 expressions and substitute them in the work-energy relationship, and if I do so, what I'm going to get is that 1/2 times m times r1 squared times omega squared is going to equal 1/2 times m times r2 dot squared plus 1/2 times m times r2 squared times omega 2 squared plus another 1/2 times m times r2 dot squared. The half and the half will add to give me simply unity, plus m times g times quantity r2 minus r1. You can look at this equation very carefully and realize that at this juncture the only unknown we have is r2 dot, which is what we're asked to find in this problem. I'll leave it up to you to plug in the numerical values. I know you got it. Best of luck, everyone.